the Center for Astrophysics and Space Astronomy at the university. So it's my pleasure to welcome him at this time and let him begin his speech. Thank you.
Well, pity me, I have to follow Rick Tomlinson. But I'm going to do my best. I don't know if he's in the room yet, but he's a true visionary, and all I can do to follow him is ramp it up another notch. I'm going to try to do that. Rick, so imagine you're now 110 years old, and we've got vacation lodges by the methane lakes on Titan, and we've got tanning salons on Mercury, and a thriving interplanetary commerce. What next? So I'm going to try to touch on that a little, but I'm also going to try to keep it real with where we're going right now and how we can define a grander future for settlements. Okay. Now, my first question, the title of my talk is rather mundane, which is what can commercial space do for science? And here's my quick answer. There's a couple of things that it can do right away. And first is the commercial space can reestablish scientists' access to space. I quote here my old friend Jim Birch from Southwest Research, who is now asking the very important question of how can we have a space program if we cannot get into space? People in this room represent our best hope of getting space science moving again by giving space scientists actual access to space. The second thing we as space scientists can do is follow the lead of commercial space. Now, you may point out that commercial space is really hardly started, and what I'm going to do is explain what I mean by that. All right, first, let's remember that space science is hugely, hugely important. It literally, in our lifetimes, has changed the understanding of the Earth, the universe, and our place in it. And so let me start with just a brief series of iconic images that have all come out of the space science in the last 50 years. And just remember how it's changed. None of this existed when I was in grade school. The pictures in Life magazine you can now do with a 6-inch telescope in your backyard. Those were the greatest images ever taken for astronomy. And now it's a whole new universe. I hope you recognize most of these. We're going outward through space, the Hubble Deep Field. Cosmic microwave background. But the launch rates are falling towards zero. The whole enterprise is at risk. You've probably been hearing about the possible cancellation of the James Webb Space Telescope. Where does that leave us? It's not a good situation, and commercial space can help a great deal. Now, I'm going to talk about this in the context of astrophysics. That's because I'm an astrophysicist and I know this area very well. It does appear to me that the problems we're having in astrophysics are symptomatic of broader problems. I know many of my colleagues in other space science fields are having similar problems, but astrophysics may be leading the way towards disaster, so maybe we're seeing the problem a little bit better. And in particular, I'm going to talk about the search for habitable planets and life on them. That's also something I'm very familiar with, and it's dear to many people's hearts. Consider Virgin Galactic. Is it really going to go galactic, or should it rename itself Virgin Interplanetary? Okay. Yeah, to go galactic, you got to leave the solar system. And instead of building Spaceship One, we need Starship One. And I've got to ask the Virgin Galactic people, do you want somewhere to land your Starship? This is the broader context of where we go after we have settled the solar system. Do we end with settlements on Mars, or do we go to the stars? First, we have to know there's somewhere to go. Now, let's face it, the solar system is a pretty dreary place if you're thinking about living there. There is nowhere outside of the Earth that wouldn't make Siberia look like a tropical paradise. Okay? We really have a problem in terms of generating, I've lost my image, but we have a problem generating interest in people going there. So, let's see, where was I going? I can keep talking, but I'm going to remember what I was doing. Okay, so we maybe I'll just have to wait. There we go. Okay. So the habitable planets that we look for outside the solar system are about 1 million times farther away than Mars. Okay? That means you need about 1 trillion times as much energy to get there in the same amount of time that it now takes to get to Mars. This is a big difficulty. And yet, as Stephen Hawking says, if we don't leave the solar system, the human race is eventually doomed. Now, not everybody agrees with that, but I think most of us understand the huge currents over large periods of time, and it's kind of hard to argue with him on. Okay, so do we know where we're going to do it? And if we find a place to land our Starship, will that drive people to figure out how to get there? Or right now, talking about interstellar travel is complete pie in the sky because you really don't know if you're just going to get there and there's just nothing interesting. It's more of the most dreary places. Or can we find a place that's really inviting? Now, the business plan is easy. If we find this planet, we double the known amount of beachfront real estate. Very easy to sell. All you got to do is figure out how to get there. Okay. Now, let's talk about how astrophysics is planned. Let's get this a little more real. When we work with NASA, every 10 years, NASA hires the National Academy of Sciences to review the status of astronomy, both on the ground and in space, and make recommendations for the coming decade. They hire the community of users. Those are mostly astronomical observers and theorists. Those of us who build instruments are considered to have conflicts of interest and aren't really allowed to make the decisions. These astronomers get together and then they choose what the priorities are. Now, you can think of this from a business perspective as a group of NASA's customers forming a focus group. Okay? Now, here's what the focus group asked for 10 years ago, 11 years ago. They created a list of astronomical missions, large missions, the James Webb Space Telescope, Constellation X to look at black holes, terrestrial planet finder to find habitable planets, large infrared telescope. Well, look at the outcome of this. The number one was started, it's still being built. Constellation X was studied for 10 years, never started. Terrestrial planet finder, studied 10 years, never started. Sapphire, largely ignored, wasn't even studied. There was a couple smaller missions. Fermi, a gamma ray telescope, that one actually got launched in 2008. And LISA, A gravity wave observatory, studied 10 years, never started. That's not a good track record for a whole decade. Now, 10 years later, we do the exercise again. Large missions. Well, first finish the James Webb Space Telescope, for heaven's sakes. Well, the status now is it's still being built, launched late in the decade, early in the next decade, or maybe canceled, we don't know. W first, the dark energy mission. Dark energy didn't exist in 2000. 10 years later it does. Probably won't be started is the word. More explorers, that probably will happen. The explorers are the fast, low-cost missions. LISA, that's the gravity wave experiment that grew from being small in 2000 to large in 2010. Probably won't be started, there's not enough money. Number 5, International X-ray Observatory, that was called CONEX 10 years ago, probably won't be started. This is what they're telling us from NASA headquarters right now. There was one smaller effort, a medium effort, it's called the New World's Technology Development Program. It's not even starting a mission, but it's 10 years of concentrated development to build that mission that can find Earth-like planets around other stars. So well, after 10 years of development, they basically gave us a mulligan, said start over again on that one. It's too important to forget. Okay, well, we assume something will happen because it's not that large amount of money. What's the outlook? Oh, it's bleak. Space science is largely ground to a halt. JWST is right under fire from Congress right now, and it will suck all the air out of astrophysics if it's canceled. I don't know what there is to replace it because all of the money in astrophysics has gone into these large missions. Almost none has gone into small, innovative stuff. And if JWST goes away, it's not clear what context remains. Okay, so we're facing a no-win scenario, our very own Kobayashi Maru. Well, what did Midshipman Kirk do? Said, let's think outside the box, let's redefine this. So that's what I'm going to talk about next and how commercial space can help in that. Okay, here's the box. It's a trend line. Since the start of the space age, capability has risen, time on this axis. Isn't this a wonderfully useless graph? It has nothing on the vertical axis. But up tends to mean harder, and yes, it's getting harder steadily. There's a relentless drive for more capability in astronomy. Otherwise, the discoveries dry up. You can continue studying things you understand, measuring the details of what's going on out there, but we want new discoveries, and that means more capability. Now, it turns out this happens in high-tech fields. This is not related just to astronomy. So what's to be done? Now, there's this wonderful book came out a little over 10 years ago called The Innovator's Dilemma. And certainly in astrophysics, we are innovators. Actually, Chas Miller mentioned this in his talk a couple days ago. He mentioned this guy, Clayton Christensen, who is a professor at Harvard. And look at the chapter title, Why Great Companies Can Fail. Okay, the thesis of his book is that customers always want more of what they're already buying, and as a result, they just want more of the same at a lower cost. That's what a customer always wants. In astronomy, that turns into what I've for many years called astronomer's disease, which is mine's bigger than yours. Not mine's better than yours, mine's bigger, right? I always want a bigger, more powerful telescope. Now, Christensen calls new ideas disruptive. So a disruptive technology enters. And then those disruptive technologies have to start small. They have to be separate from the big technologies and let them grow. And when they get good enough, The large companies realize they've overlooked something, but then it's too late. Okay? There's nothing they can do to stop the cycle. He actually discusses that. There's nothing a large company can do to offset this effect, the innovator's dilemma. Here's, in fact, these are direct quotes from his book, The Cycle of Disruptive Technologies. Disruptive technologies are first developed within the established firms. So in the case of astronomy, that means some of us who like to innovate in astronomical techniques we're working with NASA, the big company. We come up with this stuff. Now, what happens is marketing personnel then seek reactions from their lead customers. That's when NASA goes to the decadal review and asks the observers what they want next, and the observers say, we want a bigger telescope just like Hubble. Then the established firm steps up the pace of the sustaining technology they already have. Says, we got to figure out how to build a bigger Hubble. Okay? Now, this is where it gets really interesting. The new companies are formed often by frustrated engineers from the established firms, and new markets for the disruptive technologies are found by trial and error. That's what we're having a little trouble with in the sciences, because it's hard to go out and create a new firm. Then the new entrants move up market and eventually steal the customers from the established firms. Now, commercial space is here in steps 4 to 5. You're forming new companies and you're finding the new markets. And at least a couple of the new companies are starting to move up market already. You can already see this. Space science is stuck in step 2 to 3. You know, our lead customers are asking for more of the same. NASA's trying to give it to them. And me in the role of frustrated engineer doesn't know what to do next. So, now, let's look at the search for exoplanets from this perspective. Remember, NASA centers are now playing the role of the great companies. And what they've done over the last 10 years is they've put together something called the Navigator program, which is going to improve telescopes to the point where it can do this. Their goal was literally to fly missions that can reveal Earth. And remember, we just got a mulligan. They failed after 10 years. They kept developing something called the Space Interferometry mission, which was put out of business by innovation from ground-based telescopes. All those exoplanets you've heard about found from the ground until Kepler. By the way, Kepler is flying now because of the genius of one individual here at Ames, Bill Barucki, who saw the importance of the Kepler mission a decade before the first exoplanet was found, and managed to get NASA interested in it early on, and then persistence followed that. So we're very lucky to have a second way to find exoplanets this early in the game. All right, anyway, they've been trying to improve Hubble-like telescopes to the needed level. They tried an interferometric version, they tried a coronagraphic, way too expensive, and literally by halfway through the decade, many people were, it's just going to work. Okay, the problem in exoplanets is picking this incredibly faint Earth-like planet out of the glare of its parent star. Okay, that's a picture of the star Regulus. And the Earth, if you can see down in this corner, there are some stars, you know, a degree away, and the Earth is 10,000 times fainter than any one of these at the very limit of this image, and it's right there in the middle. Separating that out and doing spectroscopy of it so you know what it is, that's tough. So how are we going to build a telescope that's good enough to do that? Well, enter the disruptive technology. We know the capability we want. We've got to do spectroscopy of a 30th magnitude star, a 20th of an arc second away from a 5th magnitude star. That gives us a chance of finding an Earth-like planet. So that's a factor of 10 billion in brightness over half of a Hubble resolution element. Currently, we can do about 10,000, factor 10,000 over 5 Hubble elements, so we've got a long way to go technically. Enter the disruptive technology. 5-6 years ago, I invented, with the help of some great colleagues at Northrop and Princeton, this new disruptive technology. Got support from the NASA Institute for Advanced Concepts. That's a wonderful generator of disruptive technologies. And it got canceled a few years ago, and it's back in the Office of the Chief Technologist, and I can't tell you how happy I am about that. As a result of this disruptive technology, we got under the cover of Nature, got a patent on it, very exciting. And it's led to the concept called the New Worlds Observer. This is a Hubble-class telescope, not higher class than Hubble, comparable to Hubble. This is what we call a star shade. It's about 60 meters in diameter and flying 80,000 kilometers away from the telescope. So you can't do this in low Earth orbit. And you line the two up along the line of sight to a nearby star that might have a planet. And it works very simply. It's the same thing with catching a fly ball in the outfield when the ball's coming out of the sun. You hold up your hand, you put a shadow over your optic, and then that makes something in the glare much more visible. The trick was, though, to reduce the diffraction around this to the point where it didn't leak back into the shadow, because you need that shadow to be 10 billion times deeper than the signal that's just 20 meters away at a distance of 80,000 kilometers. The shadow is the same shape as one of Rapunzel's hairs. If you stretched a 100-meter long hair out along a football field, that's the size and length of the shadow. Very difficult to control, but it can be done. Now, we need some critical technologies developed. Here's a whole slew of them. I don't want to go into it, but remember that this thing is now about 65 meters tip to tip, and these specially shaped petals are what suppress the diffraction. Okay, I'm a frustrated scientist. We've proposed 2 architecture studies, one to NIAC and one to the Astrophysics Strategic Mission Concept Study. They were both funded. We've shown we can do this. We've identified the problems. We have a roadmap on how to move forward on it. We've also put in 7 proposals for technology development. All have been rejected. I have 0 funding for this right now. I can believe I'm frustrated. It's only the vision of a few friends like Ron Paladin and Northrop that have kept us in business while the NASA agency kind of fights the new technology. Remember, they're the big company. They can't see the value of a disruptive technology. Now, when we go outside and we talk to the focus groups, they even said, develop star shades. Star shade is a word I coined, and it says in there, do star shades, okay, as well as more conventional coronagraphs. They should all be developed, and the group was wise enough to not pick the winners. We've heard that theme here this week, and I'm a big believer in that. We've got to not pick the winners. We've got to give everybody a chance to see what they can really do. Well, the decadal review came out a year ago, no plan for a year. Last month the plan was revealed, and ta-da, let's continue doing what we've been doing. Now, to avoid Einstein's definition of insanity, got to do something different. So many of us don't think this is a terribly good plan to continue what failed last decade. Now you have to ask yourself, what can we do? Many years ago, I was lucky enough to attend a colloquium that was given by Edwin Land, the Polaroid Corporation, and he said at that point that you can often answer a tough question, but the trick is to frame the question right. So I have framed this question right. Okay. Start with what you can do. Start tiny like the disruptive technologies and start doing astronomy with them. It's the only way to develop a disruptive technology. And we have to stress demonstration. You don't start a small company and let it grow without delivering some product. And our product is astronomy. We've got to find the niche markets and then move up market. Okay? We do not attempt to compete with flagship missions. Now, this is very difficult because NASA has set up the peer review system, so that's exactly what we have to do. I can go into NASA with a proposal that says, in a 5-minute rocket shot, I can get a spectrum of this object. And then the review comes back and says, yes, but if you use Hubble for 5 days, you can get the same spectrum. So what's the point in doing your experiment? And that's just undercuts innovation. Okay? So really, we've got to find some niches where we can do some science that hasn't been done before. Now, exoplanets can, in fact, be seen with much less powerful observatories than one we eventually want. So that's one of our keys here. Here's an image of Fomalhaut. Most of you have probably seen this, taken a few years ago with Hubble. There's a ring of debris around it. And down in this quadrant here, there's some objects that appear to be planets moving. Fantastic stuff from Hubble. Here's HR 8799. This is done from the ground, and you've got 3 planets clearly visible. This is the kind of stuff we can do downscale. And here's what we've got to do. We've got to take what we want to do eventually and do a reductio ad absurdum. At the top of it, we got a full-up system, $3 billion to build this. And it's going to lead to spectroscopy of Earth. Well, what can we do that's less? How about a small system, $500 million, study the outer planetary system? Okay, that's still $500 million, and you have to move heaven and earth to get that much money out of NASA. Can we do anything without going into orbit? That lowers the cost a great deal. And luckily for our system, the separation between the starshade and the telescope is dropping as the square of the image quality required. So a suborbital system at $20 million could do the nearest stars only. And can we do anything from the ground at 100K? Well, actually, we can do that Fomalhaut giant debris disk for 100K. The question you got to ask is, can you work in the atmosphere? Okay. Well, actually, yes. Lab tests can be done, 40,000. They're already done. Now we've deconstructed. Let's reconstruct and move our capability up market. Let's see how we're going to do that. All right, already working in the lab. This is actually showing a starshade from behind, backlit in a coronagraph facility at the High Altitude Observatory. They work. Now we're going to do astronomy with a starshade about this big. We can hang it on a frame, put it on a mountaintop, and we can blot out Fomalhaut and see the ring. This is a simulation. We're doing this right now on our own nickel, and hopefully within a few months we'll have an image like that simulation there. Next step, let's go to suborbit. This is where we can really get a ride from the various kinds of new capabilities that are being developed in commercial space. Balloons and dirigibles. Balloons allow greater separation in a quieter atmosphere up in the stratosphere than we get on the ground. Separate a starshade hanging from a balloon from a telescope hanging from a balloon, and you've got 300 kilometers separation. Okay. And then down here, an Earth-like planet shown around Alpha Centauri. It's possible. Am I running out of time or something? Yeah. Okay. All right, so this is definitely moving up market. This can be done for $20 million. We can map the Alpha Centauri system. The Maston Zero, we put in a proposal in January for this, worked with Maston, and what we saw was we can hang a star shade and fly it above a telescope on the ground. We can get 1 to 300 kilometers separation and do the Alpha Centauri problem for a few $1 million. NASA said no, we don't know why. We think it's a great way to both develop the Maston system, its capability for precision flight, and do some science that's needed as well. Still a big leap from suborbital to a flagship, so we should fly an intermediate-sized one with a half-meter telescope, 10-meter star shade, $500 million range. You could get pictures like this of the nearby stars, that's Jupiter, Saturn, and so on. And then finally, you're ready for prime time. This is a simulation of what the full-up mission would do. There's your block where the star shade is. That's the Earth. That's Venus turned down because Venus is actually much brighter than the Earth. Get to play God a little. You can just make Venus smaller. This is Jupiter in a crescent phase. And then you do the spectroscopy. This is the Holy Grail because that's the Earth. This is a simulated spectrum. You see the water features. You see the oxygen features. This is a planet that has life. That's Jupiter. That's got methane and all kinds of nasty stuff in it, and that's not where you want to land your starship. So if we do this, the 2020 Decadal Review will give us a chance to build a really big mission because we'll have done a slew of astronomy by the end of the decade. We've proven it can be built. It will not overrun, it will achieve the astronomy goals, and there is an experience base for the mission. This is one thing we must always have is an experience base. You can't go after a big project without people who already know how to do it. And at that point, the disruptive technology will have won over the customers. So back to the original question, what can commercial space do for science? Well, cheap access to space allows us to develop the experience base. New launch capabilities will support new science in often in unexpected ways, like with the Maston carrying a star shade. And finally, you guys can break a path for developing disruptive technologies for space. And together we can really do amazing things. Thank you.
Thank you very much. Now for our next panel, we'll be leading off, introduced to
For astronomy. And now it's a whole new universe. I hope you recognize most of these. We're going outward through space, the Hubble Deep Field. Cosmic microwave background. But the launch rates are falling towards zero. The whole enterprise is at risk. You've probably been hearing about the possible cancellation of the James Webb Space Telescope. Where does that leave us? It's not a good situation, and commercial space can help a great deal. Now, I'm going to talk about this in the context of astrophysics. That's because I'm an astrophysicist and I know this area very well. It does appear to me that the problems we're having in astrophysics are symptomatic of broader problems. I know many of my colleagues in other space science fields are having similar problems, but astrophysics may be leading the way towards disaster, so maybe we're seeing the problem a little bit better. And in particular, I'm going to talk about the search for habitable planets and life on them. That's also something I'm very familiar with, and it's dear to many people's hearts. Consider Virgin Galactic. Is it really going to go galactic, or should it rename itself Virgin Interplanetary? Okay. Yeah, to go galactic, you got to leave the solar system. And instead of building Spaceship One, we need Starship One. And I've got to ask the Virgin Galactic people, do you want somewhere to land your starship? This is the broader context of where we go after we have settled the solar system. Do we end with settlements on Mars, or do we go to the stars? First, we have to know there's somewhere to go. Now, let's face it, actual access to space. The second thing we as space scientists can do is follow the lead of commercial space. Now, you may point out that commercial space has really hardly started, and what I'm going to do is explain what I mean by that. All right, first, let's remember that space science is hugely, hugely important. It literally, in our lifetimes, has changed the understanding of the Earth, the universe, and our place in it. And so let me start with just a brief series of iconic images that have all come out of the space science in the last 50 years. And just remember how it's changed. None of this existed when I was in grade school. The pictures in Life magazine you can now do with a 6-inch telescope in your backyard. Those were the greatest images ever taken.
The Center for Astrophysics and Space Astronomy at the university. So it's my pleasure to welcome him at this time and let him begin his speech. Thank you.
Well, pity me, I have to follow Rick Tomlinson. But I'm going to do my best. I don't know if he's in the room yet, but he's a true visionary, and all I can do to follow him is ramp it up another notch. I'm going to try to do that. Rick, so imagine you're now 110 years old, and we've got vacation lodges by the methane lakes on Titan, and we've got tanning salons on Mercury, and a thriving interplanetary commerce. What next? So I'm going to try to touch on that a little, but I'm also going to try to keep it real with where we're going right now and how we can define a grander future for settlements. Okay. Now, my first question, the title of my talk is rather mundane, which is what can commercial space do for science? And here's my quick answer. There's a couple of things that it can do right away. And first is the commercial space can reestablish scientists' access to space. I quote here my old friend Jim Birch from Southwest Research, who is now asking the very important question of how can we have a space program if we cannot get into space? People in this room represent our best hope of getting space science moving again by giving space scientists